Voilà. Okay, so we can start. I want to show you two things on the computer. You're going to get the statement of your fourth assignment. It's going to be one question. Of course, we will see how the finite element method is developed, but we don't have much time left, so I'm not going to expect you to implement the method, but we will run simulations in FreeFM. So for this assignment, it's going to be an elliptic problem with some convergence analysis and things like that. Anybody used FreeFM before? Yeah, I know there is a couple in the classroom. So the first thing you have to do to get ready for the course, let me check if I'm... do we have the sound, people online? Do you have the sound?
Yes.
Oh, okay, good. Okay, so the first thing you have to do is to install FreeFM and start reading the documentation and run test case. So I want to show you how it works. So if you go to the FreeFM web page, you can just Google FreeFM and then you're going to get to it. So the documentation you can get there. Be careful because there is the old version here and then there is the current version. So I want you to download the current version of the thing. Now, after that, in there, be careful because there are things you can download from there, but that's a very old version. You don't want to install that version. So you just go there to get the documentation, and then you don't need to stay there after that. Now, the download area is going to give you the place where you can actually download the most current version of FreeFM. I guess that most of you, unless you are really interested in compiling the whole thing, it's a long compilation. It can take up to an hour to compile with many steps to do. And even for someone experienced, it does not always work. It's a bit difficult. So my recommendation would be that you install the executable, so a binary file. And then you have a Windows version, and then you have here, I think this one is a Mac OS version. And you have the source code. Now, from the source code, you will be able to get examples. So if I download the source code, I'm going to put it in that folder and then go there because I want to show you something. There are examples in the documentation that you can run and that you will be looking at to get ready for the next assignment. And this is in the folder. There is this subfolder called example. This is where you have to go to get all the examples. And in particular, examples, you get the examples from the chapter 2 or 3 of the documentation. And the first few examples are membrane. I'm going to open that so that you see the piece of code to do finite element simulation is relatively simple. The way it works usually is that it's split in different software. There is a software that carries usually a library that carries the finite element simulation, but you have to prepare data to run the simulation. This is usually done in a pre-processing step where you generate a mesh. And once you have this mesh of the geometry, you run the finite element software, and after that, you output data into files, and then you read these files in a post-processor that is a graphical package that is used to run simulation. In FreeFM, you can do that, but again, to make it simpler, it's also all integrated. So everything is on the pre-processing, the processing, the finite element computation, and the post-processing, the visualization can be done in the same package. So that's the nice thing about that. So if we look at this simple example, this is the definition of the geometry. This is the definition of the finite element space. You will recognize over here the variational formulation in principle. It's grad U, grad phi, grad W. That's the variational formulation for the Laplace equation. This is where you impose boundary condition, and then this is where you do the post-processing. You plot the solution, and then have this eventually output into files, and that's it. You're done with the simulation. Of course, this is for a simple problem. My hope is that I'm going to give you a problem that is a bit more challenging, but you will be able to start from some file that you have there. Now, what else do you have to look at? So once this is where you get the source, this folder where you have the source, you will need only to get the source, the examples that are discussed in the textbook. If we go now to the textbook, I'm just going to show you what you have to read. The textbook is quite thick. The textbook, the documentation is quite thick, but you're not going to have to read all of that because there is a lot of material to read there. I'm just going to indicate what you have to read there. So that's the FreeFM documentation. That's the one I imported from the web yesterday, from the website yesterday. So you have I have the latest version, 11 of March, that cannot be more current than that. And what do you have in there? Of course, you have the people who developed the code. So in the introduction, you have a bit of the history. You have an installation guide, section 1.2. My recommendation is that you go on the web to get the latest version of that. I don't know how up to date this one is. I figure it is relatively up to date, but I don't know. So my recommendation is that you follow the instruction online. If you have difficulties, there are so many people, there are thousands of people using FreeFM around the world who have probably the same issue that you're having now. Google the specific bug that you get when you try to run the code, and eventually you'll get comments online about that. Now, the chapter that you have to read is chapter 2, learning by examples, where you have tons of examples. You have membrane, that's the Laplace equation. Heat exchanger, it's a fancier version. I think acoustics, it's the Helmholtz equation that I discussed a bit. And then you're getting to pure convection and things like that, fancier fluid dynamics problems. So probably if you read from page 33 up to maybe 50 or 49, you're probably good starting running. Now, if I go to I go there and I have a look at what you have there. There is a bit of an explanation on how FreeFM is working, two different ways to define a variational problem. We're going to probably look at the easiest approach, which is using problem rather than var f and matrix, where you're defining the matrix on the right-hand side instead of just having the whole variational problem formulated in one shot. And then from there, they start explaining the header of the file, how you define the geometry, how you define the mesh, how you define the finite element space, how you run the simulation, how you do the post-processing. And they start with a very simple problem, the Laplace equation with Dirichlet boundary condition. So if you want to run that, that's the one you can probably get in the folder that I pointed to, the folder example in the source directory. This is where you can probably get all these functions. So you don't have to copy paste and create files for that. Now, one thing that I'm not using because I run on Linux and I run in the terminal, there might be a front end to use FreeFM. I know that some of my students, they installed FreeFM on Windows machine, and then I don't know if it's coming with the current version of FreeFM. So you're going to have to see. If you have difficulties, come and see me and we'll find a way to have this work. But I figure that once you have the thing installed on your computer, it's going to probably work. You will have the thing with an icon and you will just click on that and start FreeFM. And then, so my recommendation till next week is to spend some time trying to first install the FreeFM and start running the example in chapter 2 so that you get ready working. And everything is done inside the code. So that's going to be, you're going to get that kind of visualization. You can eventually, I'm going to come back to that. I will show you one example later once we have done 2D finite elements. But you can start looking and try to run. By the way, if you go on the FreeFM web page, there is try it online. So you can go and try it online there. So there is this little example, which is solving the Laplace equation with u is equal to 0 on the boundary, and then you can run and see the solution. relatively coarse mesh. Let's refine the mesh. So N is controlling the mesh quality. Let's put 50 elements instead of only 5. I don't even have to save that, and then it's rerunning the thing online for you. You can change the type of element. I'm going to move to quadratic element here. So you can do everything like that, but this is for this simple example, just so that you try the thing. I think that at one point someone came to me, a student in a previous course, and then say, oh, you know, I found a place where I can run FreeFEM online. That might exist. I don't know. I don't recall if it was for Octave or for something else. We can change the boundary condition. Let's put some other boundary condition. Let's put X on that thing and then see if it's working when I run. It sounds like it's in a loop. Let's go back here. Let's try online again. Let's put X here. Let's put more elements, but certainly not P2. Let's put 10 elements. And let's see how it's working. If I put X, you see you're getting the boundary conditions to work in that case. You see, you can run simple things like that. Of course, the goal is not to run in this way, it's to install FreeFEM on your computer and run things on your computer. That's why I spend so much time discussing variational formulation. It's because when you get to use the software, you're going to have to basically set your variational problem, and that's going to be relatively easy. Do you want to implement the finite element method? Do you want to have an assignment like that? You did it already, eh? It's long. Eh? It takes weeks to actually debug your code, especially if you do it in 2D. It's a bit challenging. So that's why for the course I was, my expectation at the end of the course is that you can write, you have a PDE problem, you can write a variational formulation, you can write the code, and you can get solutions. If you learn this from the course, that would already be a starting point, but you're gonna know that a bit what's going on in the background, because I will explain how things are done in there is a lot of computation carried in the background because you have a mesh. You see kind of a bit of the mesh here. This is the mesh in the background. So we're going to have to find a way to represent this in the computer. There are data structures that are involved to represent the information in the computer. Everything has to be organized. How we store the unknowns, how we store the mesh, what is the connectivity between the triangles and their neighbors and things like that. That needs to be, and we'll start first in 1D because it's simpler, and then I will go to 2D after that. So a bit of the emphasis of the way I present things is going to be on how things are done in the background, but in terms of application, it's going to be simpler because it's going to be in the software. Any question on that? Okay, so one thing that I did yesterday is I had a script for the Fisher equation that was in mini project 2 online. If you have downloaded the thing yesterday, download again, because I had a new version about an hour and a half ago. There was a bug in the one I've given you. I run the scripts on different computers, and sometimes they work and sometimes they don't work. And when I tried on this computer, there was a bug remaining that I removed, and I did a bit of update. So let's go to that thing now. Let's go to, I think I have this here. Yes, let's start Octave. And I want to show you what the kind of expectation I had for mini project 2 and problem 2, question 2, in terms of the accuracy that I would have expected. You did all less than that, but personally, when I want accuracy, I want accuracy. I mean, 1D, I put 10,000 points if I need 10,000 points, and I let this run. So this is the script I implemented. I started from the script eat that I provided to you. And I just did a little modification. We already had the matrix. We looked at that. That's the matrix A for representing the diffusion in the system. And then I have a switch. M flag is for the method. And I've implemented 3 methods. The forward Euler time stepping. I write backward Euler. It's not backward Euler. It's the semi-implicit method. And I write Crank-Nicholson. It's kind of Crank-Nicholson for diffusion, but it's fully explicit for the reaction term. So it's not actually truly Crank-Nicolson. But let's go and see how I did things. So one thing that many of you did is that they had the diffusion matrix, and then they generated the identity matrix using the command I. There is a special command for generating a sparse identity matrix, which is a SPI instead of I. So that's a sparse I that you should use. So those of you who use I, you are actually having A as a sparse matrix, and then you're generating a matrix, an identity matrix that has 1 on the diagonal, 0 everywhere else, but it's a full matrix. So basically, you're using a lot of memory. So if you go for a very fine mesh, it's going to have an impact. On a small mesh, okay, but on a big mesh, it's going to have an impact. Now, once I have that, instead of actually using the LU factorization, the matrix A is symmetric. The identity matrix is symmetric. The sum of the two is symmetric. So instead of using the LU factorization, I decided to use the LLT factorization. If you don't know about that, forget what I'm saying. Just see the code that is there. But if you can do help and go in the document and see what is the Cholesky factorization in Octave, and then eventually read on Cholesky factorization. Basically, it's factoring the matrix A when it is symmetric as a lower triangular matrix times the upper triangular matrix. That is just the transpose of the other. So A is equal to L times L transpose. And then in this way, you have a simpler way to solve the system, and you have less storage for your matrix. So you save a bit of memory. We're in 1D, it's not so important, but eventually that may make a difference. So now the thing that I have for forward Euler, I have no matrix to factor. For backward Euler, I have to factor the identity plus the diffusion matrix. And for Crank-Nicolson, that would be the identity plus 1/2 times the diffusion matrix. And when we get to iterate, if I iterate the forward Euler, I'm doing this way. Many of you implemented exactly in the same way. If I want to iterate the semi-implicit method, I would do that. And then for the Crank-Nicolson, I would do this thing. It's not a it's Crank-Nicolson for the diffusion, but unfortunately, Crank-Nicolson would require that I would take 1/2 of this source term f at time n and 1/2 at time n plus 1. So that would be a fully implicit method. And this way, I would get second order accuracy in time. If I'm taking explicitly f, even if I treat the diffusion term as a la Crank-Nicolson, I'm getting second order on the diffusion, but I'm getting only first order on the reaction term on f. Unfortunately, it's going to be, the end result is going to be a first order method. So I have it here. I'm not using it, and I didn't ask you to go in this direction. Although one or two person in the classroom opted for this method because my question was kind of open. Now, let's see what we want to do. I want to just show you the kind of expectation I had. Notice this thing. There is a way to clock the CPU time. So you just have a tick. You say, give me the initial time of the CPU, and then just take the difference at the end. So just do elapsed time. When I don't know how to do something, I just how to get CPU time in Octave, and you get up to a page where it's done for you. And then I just copied the two lines, and then what it's going to do, it's going to compare the time, the clock time on the computer at the beginning and at the end of the computation, and you get the difference between the two. So let's run three things. I'm going to run, so for the question C, which was nu is equal to 10 minus 5 or something like that, I'm going to use 10,000 points in 20,000 points in space. That was the order of what I would have expected if you want your graph to be very close to each other. And I'm going to use the largest time step I can use to make the method work. Of course, for the explicit method, I'm going to have to use a very small time step. And M flag is what? M flag is the method, 0 for explicit and 1 for semi-implicit. Okay, I'm going to run the three method, and we'll see what we get. So I have here, that's this one. That would be kind of a reference. That's the semi-implicit, 20,000 grid points in space and 40,000 time step to get a relatively good solution. Okay, so while it's iterating, I'm going to do one thing. This is going to be in blue. That's the first solution. It's in blue, and now let's change the color to have what? To have the same thing, but this time in, it's in black. Let's put it in blue for the backward Euler, but with a larger time step. Where are we now? You see, I'm having the fourth solution, and it took me 32 seconds to get the solution of this mesh. Now let's compare to see. You will see that there is no way to beat the semi-implicit method. I'm going to do the same computation again with semi-implicit, but I can use a time step that is 10 times larger than the other one. And you will see there will be a bit of an impact in doing that. But certainly the nicest thing is that I'm getting the solution 10 times faster. That's the expectation, because my matrix is factored, so it's behaving linearly in time in terms of the CPU time. And let's see how great is the solution. You see the curves are almost superposed. I'm going to zoom later on, and you will see that not exactly. And now let's see how long it would take if I do fully explicit method. Now, if I do fully explicit, unfortunately, the time step that I have to use is even 10 times smaller than what I had. I had delta t is equal to what? Is equal to 10 minus 3. I need to use 10 minus 4. If I use 10 minus 3, you have to believe me, it's unstable. So that means the CPU time is going to be huge. I forgot to change the color, unfortunately. Unfortunately, I should have. See the CPU time it's taking. It's going to take forever. So, and then let's go and see the solution that we have. Unfortunately, I should have changed the color. I should have put red. I hesitate to stop the thing. It's just so slow. So 3 seconds is the 32 seconds is the time to beat. You'll see that with 3 seconds, I'm a bit off. So if I increase the time step, of course, I remain stable with the semi-implicit method, but unfortunately, the solution is going to start deteriorating. The larger is the time step, it remains stable unless you take very large, but it remains stable, but it's becoming less accurate. But the semi-implicit method the explicit method is just taking forever. You'll see it's going to take about 3 minutes to calculate. So we're far off if you're using a fine mesh. So I would say most of you went to 1,000 points, some maybe 2, 3, 4,000, not much beyond that. Personally, I'm not completely happy with a solution that is not. Let's zoom in to see where we are with the computation. You see the one that is off here is the semi-implicit with the larger time step. There is more error actually involved in using a larger time step than there is in actually in space. I'm using the same grid in space. As there is more error involved in using a larger time step than actually changing the method. Because with the smaller time step for the semi-implicit method, my time step is already quite small, so the convergence is already quite good. What would be the most reliable one? That would be the one with the explicit method, but the problem is the CPU time. The explicit method is using a very small time step. You see the elapsed time, so I'm about 5 times more expensive than with the semi-implicit method, basically. if I have to go for very fine. Now let's see in terms of accuracy. You see that I'm going to zoom again just to see what's happening. So we're having in principle 3 curves. Unfortunately, 2 have the same color. So the one that is behind is the semi-implicit with the larger time step, and the 2 methods, the semi-implicit with the small time step and the explicit method are almost superposed at that point. So I have, and what would be the accuracy here? We can have an idea of the accuracy. You can look at the difference between these 2 solutions. We're getting about what? We're getting, I would say, it's on, the accuracy is only on the 2nd or the 3rd digit. It's not any better than that. So that means with 20,000 grid points and very small time steps, you're getting an accuracy of about probably, I don't know, what would be, this is like, yes, this is 0.1. We're getting an accuracy of about 5% on the solution here. This is what it means. So 5%. If you consider that this is a model for population dynamics, if you have 5% accuracy on the numerical method, you're probably right on the model, because the modeling error is probably larger than the numerical error. Being aware that sometimes the dynamics of the solution is wrong if your mesh and time step is not, your mesh is not fine enough and you don't use a small time step that is small enough. When you try to catch fine dynamics at the limit of stability and instability, sometimes you need to use very, very fine mesh and very small time steps. Here we don't have this issue, but still the evolution of the wave is such that the waves are splitting apart. As the waves are traveling, if I go back, it's hard to judge on the solution here, but the distance between the solution here, if I don't know, I will try to zoom on that. I don't know if we will be able to see. You see that the distance is progressively growing between the solutions. See between these 2. You see the distance, it's hard to see, but the distance is growing. So the speed of the wave is actually wrong. If you use a space and time step that are too large, eventually your wave speed is not going to be correct. That's the kind of issue we get with this kind of problem. Any question on that? No? Okay, so then I will stop this. Let me stop this thing. Let me go stop share. This one. Okay. Anyway, so it's just to show you. I will provide you a solution for question 1. I said I would and I will, but I did not have time to do that. Let's share this. Okay, so let's go back to now to paperwork. So what do we want to do? So today we want to do 1D finite elements. So I want to introduce you all the data structure and how things are done with finite element method. Okay, so that's our so 1D finite element method in dimension 1, FEM finite element method. What is my model problem? I'm interested in solving this problem, for instance, which would be, let me see, yes, minus A U prime prime plus CU is equal to F, say on the interval 0, 1. I would have U of 0 is equal to 0 and U1 is equal to 0 as well. So that's my model problem. So that's the Laplace equation in 1D. So what do we need to start with? to define our finite element method. So we consider a partition. Usually, a partition is called a mesh, in fact, for us. A partition of the interval of 0, 1, of the interval 0, 1. And this one I'm going to take as that. So you will have x null is equal to 0, which is smaller than x1, which is smaller than x2, which is smaller, so on and so forth, to xn minus 1, which is smaller than xn, which is equal to 1. So I'm having n space points. So that's the mesh. K R that goes from what to what? That goes from xr minus 1 to xr is an element of the mesh. So R goes from what to what? R goes from 1 to capital N are the elements of the mesh. Of the mesh. So I'm defining all the notions that we need to define our numerical method. So we need a parameter that is going to characterize the size of the element. So set what? Set HR is equal to what? Is equal to HR minus 1. So the size of the element. And we do this for every element. And then I want to have the maximal size, which is going to be the max of HR, where R is going from 1 to N. So that's the maximal size. So that's going to be defining the accuracy of the method. Now we're ready to define the finite dimensional space. So define the finite element space as that. So that's one particular instance of finite element space. I'm not saying that that covers all finite element space. So I'm going to call it VH. So I want my function to be in the set V. Recall that for this thing, I'm getting what I'm getting in this situation, that V is equal to what? V is equal to H1, 0 of the interval 0, 1. Okay, I'm getting that. So I want my function VH to belong to what? To belong to V. So this way I can impose the boundary condition inside the space, such that we're having what? Such that we're having that VH restricted to every element KR is what? Is a polynomial. Is a polynomial. I'm going to set polynomial like that. P, let's use L on the element KR. So I'm going to say, and then I want to have the function VH to belong to C0 of the interval 0, 1, like that. I said last time that I wish to have functions that are continuous. There are discontinuous finite element method, but I want to have in 1D, I know that in 1D, H10 is embedded continuously in C0 of 0, 1. So that's a natural choice to pick functions that are continuous. And moreover, the advantage of that is that there is a theorem saying that if I have functions that are polynomial on each element and continuous across the boundary, they do belong to H1. In fact, it's possible to say that not only in dimension 1 and more than that. Where I'm having what? Where PL, this thing on KR, is the space of polynomials of degree L on the element KR. Okay, so in particular, if L is equal to 1, in this case, we say that we have linear finite element, which I will abbreviate like that, finite element. And in this case, what do we have? My function would be something like that. So I would have the mesh. Note that the HR need not be here all of the same size. So the size of node, the HR are node, HR need not be constant on the mesh. All the same, need not be constant over 0, 1. So I can use smaller values of HR where the function has large variation and larger elements where there is less variation in the function. So that's a slight deviation from what we did with finite difference. But when HR is constant, there is some expectation that we will eventually recover the finite difference method. Okay, so we'll see that. So if you look at the function, if I'm whether or not, so x null, x1, x2, so on and so forth like that, you're getting what? You're getting the function to be something like that. 0 or not, depending on the boundary condition at x null, and then you're getting a function that is linear like that. So that means on every element, what do you need? So that's the element, that's xn here, and that would be kn, and your function would be linear like that. While if I use quadratic elements, so that what do you need on every element? You need on every element to specify 2 values of the function to completely specify your function. When L is equal to 2, we say that we have, in this case, quadratic element. These are the most popular one, quadratic finite element. These are the most popular one. And then in this case, on every mesh, on every element, we're getting a quadratic function. And to specify the value of the function, we need to add the midpoint eventually. And on every element, you will have 3 values to specify the function like that. You will get eventually something like that here, and then that would be, say, like that. We're getting the continuity of the function by choosing the degrees of freedom at the endpoint. So that's my mesh, my element K1, my element K2. That's the node x0, x1, and so on and so forth like that, all the way to xn, and that's the element kn. So there are 3 degrees of freedom per element. So here we're having 2 degrees of freedom by element. 2 degrees of freedom per element. While here we're getting how many of them? We're getting 3 degrees of freedom by element. But they are shared with the endpoints are shared with the neighboring elements. But that's going to allow us to, so by element, we're having 3 over here. And if you keep going like that with cubic finite element, you would get 4 degrees of freedom by element. So if I look at the dimension of the space VH without Dirichlet boundary condition, so what do you have to provide here? You have to provide the unknown like that. So I could label the unknown like that. They could be U0, U1, U2, and all the way up to UN. While here I would need to add middle nodes. I'll do it later. I'm not going to do it right now. Now, what is the dimension of the space without imposing U0 is equal to 0, and without imposing that, so letting these nodes to be free. So without imposing that, what is the dimension of the space VH? That's the number of node. That's the number of node that you have. And then when I'm linear, there is no internal node. So that would be the number of node. So n plus 1, the dimension. While if I use quadratic element, that would be the number of element times 2. Because this one is actually, these 2 are attached to the first element, these 2 are attached to the second element, so on and so forth. And then there is only a last one remaining at the end. So that means it's the degree of the polynomial times the number of elements. So that's going to be the number of elements, which is n, the number of elements, times what? Times L minus 1, plus the number of nodes. So let's write it this way. The number of nodes xi plus what? Plus the number of internal degrees of freedom, just to see what is the dimension of the space. So the number of node is n plus 1, plus the number of internal node is going to be the number of elements times L minus 1. So when L is equal to 1, there is no internal node. When L is equal to 2, we're getting 1. So that means that the dimension of the space is n times L plus 1. Now, if I impose the end values to be 0, so if I impose U0 to be 0 and U1 is equal to 0, so that means that the dimension is going to be reduced by 2, so we're going to get what? We're going to get NL minus 1 in this case. So that means if we use linear element, I'm going to have n minus 1 internal nodes, so degrees of freedom. If I use quadratic element, that's going to be 2n minus 1, the size of the linear system, and you keep going like that. Okay. Now, this is, in this case, I'm having homogeneous Dirichlet boundary condition, so that means that I'm going to have to reduce the size. A remark here is that in general, in finite element code and in FreeFEM in particular is working in this way. We always implement for Neumann boundary condition, and then we impose the boundary condition a posteriori instead of imposing it directly. Because if you impose the Dirichlet boundary condition directly, you're going to have to change the dimension of your linear system. The number of unknown is going to change, and that would require a different assembly process for Neumann and Dirichlet boundary condition. And if you want your finite element code to handle both Dirichlet and Neumann boundary condition without too much pain, usually it's easier to implement for Neumann and then enforce afterward the value of the function at the endpoints. In FreeFEM, to be honest with you, I don't like the way it's done because it's done by penalization, which is not the best way to do it. I'm going to explain this later. And then think about the situation where in 2D you'd be like that. If you have a very thin geometry like that in 2D with very few, we're going to use, for instance, triangle with very few internal nodes. Most of the nodes lie on the boundary. So if you keep them in the system, the size of the system for Neumann boundary condition is much larger than what you would have for Dirichlet boundary condition, getting rid of the degrees of freedom on the boundary. So that has a practical consequence. Assembling for a Neumann problem and then imposing afterward the Dirichlet value on the boundary has actually an impact on the size of the linear system that you have to solve, and that could make it a little more challenging if you have very thin geometry, and sometimes we have that in applications, very very thin geometry. Okay. So that's a thing to remember. Now, what do we want? That's just a remark like that. So what do we want? We want a basis for the finite element. We want a basis. So we want to write what we want to write. To write our the unknown VH or the test function of X as what? As a sum of VI times test basis function X, like that, where I is going from 1. In principle, that would go from 1 to what? 1 to NL plus 1. Depending if I'm doing Dirichlet or Neumann boundary condition, where phi I is a basis, is properly chosen, is a basis. So we call them basis function. properly chosen. And properly chosen, I want my matrix to be as sparse as possible. That's the thing we want. So we want what? Properly chosen, meaning this, meaning that the matrix have to be sparse. The global matrix have to be sparse. And to do that, how are we going to do that? We are going to do it in this way. So we're going to have so the strategy is to do what? The strategy is to pick the support of the function. So the support of the function of the phi I. You remember what is the support of the function? That's the set where the function is non-zero, to be the smallest as possible. That's the way I will be able to enforce the sparsity of the matrix, to be the smallest as possible. That's the way we want to do it. And moreover, so that's one condition we want that's one condition we want to impose. So that's one thing. And the other thing, we want a nodal basis. This is not essential, but that's going to be a basis. That is a basis satisfying what? That is, we want to have that vi or u h of xi equal to the sum of what? Equal to the sum of j going from 1 to something, to the total number of degrees of freedom. Let me write it this way. uj phi j of xi. I want this to be equal to what? I want this to be equal to ui. I want this to hold. That means what? That means what? This is equivalent to have which is equivalent to have that phi j of xi is equal to delta ij. So that means it's equal to 0 if I is different from j. Okay, the n is equal to 1 otherwise. This is what we want. This is called a nodal basis. All bases do not necessarily have to be nodal basis. They could be non-nodal. I will give you one. I will first give you the nodal linear basis and the nodal quadratic basis. And then after that, I will give you a basis that is not nodal. Everyone knows the non-nodal basis. Hierarchical basis, did you do that, Mohamed? No, hierarchical, I will give you the basis. Sometimes it's interesting to have a linear basis and then add only the functions that allows you to go from P1 to P2. And then you add something. So in that case, you have a non-nodal basis. So not all bases are nodal. There are finite elements where it's not possible to find nodal basis. But here we're using simple element. These elements have a name, by the way. These are called Lagrange elements. Because I'm involving what? I'm involving only the value of the function. I'm not involving the value of the derivative of the function. So if you know Lagrange interpolation is involving the value of the function only. And if you want to involve the value of the derivative of the function, that's Hermite interpolation. So we can define Hermite element from involving only the value of the function. So now let's define the nodal basis. So the nodal linear basis. Usually we say the linear finite element, linear basis function, what they are. So we want to see what these would be. And I will do the quadratic after that. So you have your mesh in this way, x null x1, x2 like that, and you keep going xi like that. And then let's have it not too large. And then what would be the basis function over here? So I want to have a function that takes the value 1 over here and takes the value 0 over here, and then 0 elsewhere. And similarly, for that node here, I'm going to have the value 1 here, and I want to have a function that takes the value 0 at that point and 0 everywhere else. And then this one is going to be phi I of x, and this one would be what? Would be phi 0 of x, in case I need to include that function because I'm doing Neumann boundary condition. If I'm doing Dirichlet, these two endpoints are not included in the finite element space. And you would have other ones like that. So now how do I define this one? I need a function to be. So remember that this element is what? This element is the element I'm having, the element chi a over here, and this element is chi a minus 1, and then that's chi a minus 2 over here. I don't need this one. Okay, so what do we have? So I'm going to have that phi I of x is going to be equal to what? It's going to be equal to this thing. So what do we have? I'm having on the element, there are two elements where it's non-zero, and everywhere else it's 0. By doing that, I'm going to enforce that the support is small. That's the smallest support. I want to have a function that is continuous, and I want to be the support to be the smallest as possible, and I want this to take the value 1 at xi. That's the smallest support I can have. Any other function that I pick, taking the value 1 here and being continuous, is going to have a larger support than that. So that means that the only function I can take will be non-zero on the two element neighboring xi and be 0 else everywhere else. Okay, so that means we're going to have what? We're going to have, I need to take a value 1 at 1, so that's going to be x. So this node is xi minus 1, and this node is xi plus 1. So what do I take in that case? I'm going to take, it's going to be x minus xi minus 1, because it needs to be 0 at xi minus 1, and it needs to take the value 1 over here. So what do I divide by? I divide by what? By hi minus 1, the size of the element ki minus 1. This is true for x in ki minus 1. I remember that, recall that this element is equal to xi minus 1 xi. Is it that? Actually, it's wrong. This is the element ki, and this is ki plus 1. This is wrong. So this is ki over here. And then I would have exactly the same thing on the other element, but with a different sign. So it's going to be xi plus 1 minus x, and this thing takes the value 0 at xi plus 1, and then it takes the value, so I need to divide by hi to get on the element ki plus 1. That goes from what to what? That goes from xi to xi plus 1, like that. And then it's 0 elsewhere. And I have the basis function. These functions have an a. They are called, because they have the form of an at. So these are called the at functions. Usually these are called the at functions because they take the form of a at. Okay, now we want to do the quadratic. So the quadratic would be what? In the cubic, you will be able to figure out what are the other ones. So I want to have the nodal quadratic function, quadratic basis function, which are also called the at functions, because we want to avoid the nodal basis function. We call them the at function. It's just another way to call them. So what do we want in that case? I'm going to have this thing. My elements will be like that. I will have two elements, xi minus 1. So that's which element is that? This is the element ki, and I'm having the element ki plus 1 over here, and then that's xi plus 1. And then I need to add the middle points, the middle point that I'm going to denote as xi minus 1/2, and then xi plus 1/2. This would be the midpoint. So the xi plus 1/2 are the midpoints of the element of ki plus 1. Okay, that's the midpoint of the interval. And then the basis function will be chosen. There are three basis functions. There is one that would take the value 1 here and 0 at the other points. So it's going to be like that, quadratic, like that. Notice that it's going below 0. That's a drawback of the thing. It's going below 0. Now the other basis function is going to be between two elements. No, there is these middle ones that you have like that on the element. There is this one that takes a value 1 here and then that goes back to 0. So that's another one. It takes the value 1 here and 0 at the other 2 points. And then the next thing is going to be what? It's going to be like that, going to 1 over here. And this one overlaps two elements, because it has to be like that to enforce the continuity. So it's overlapping two elements. So this one would be phi I, and I can keep going like that. You would have again another one over here, like that. So this one is what? This one is phi I plus 1/2 that you would usually remember in a code. You would not number them I plus 1/2, but you would have another numbering. So this one is phi I. This one is phi I. This one will turn out to be phi I minus 1, minus 1/2. And this one would correspond to what? Would correspond to phi I minus 1. And it would be, there would be another part that is coming over here. And you keep going like that. Now, once you have to write that, you have to just use Lagrange interpolation. How do you do that? So this it's done in this way. So on the elements, so on ki plus 1, I'm just going to write on ki plus 1 what we have. On ki plus 1 is it's going from xi to xi plus 1. On this thing, the function, let me write the function phi I is equal to what on that element? So it's going to be equal. It needs to be 1 at that point, and it needs to be 0 at the other point. So you would have what? You would have xi plus 1 minus x. That's for one thing. So this thing is equal to 0 at that point. And then xi plus 1/2 minus x to be 0 at that point, and it's going to be positive everywhere. This is positive here, this is positive here. And then now I need to get this value to be equal to 1, and then to do that, you're going to divide by what? You're going to divide by hi plus 1. For one thing, for this one, it's hi plus 1 times hi plus 1 divided by 2. So that's what you would get for your basis function. And you can keep going like that for the other one. So let me just, I'm not going to give all of them. You'll be able to develop them if need so. Be aware that you need to enforce the continuity. We'll see how we proceed with the assembly process. We will assemble by elements, and then we will put the contribution in the right location in the matrix to precisely handle the continuity between elements. But now what is interesting is that all the this one, I mean, you need to do this one, you need to do the same thing that would be on that element, but you need to do the same thing on the element ki, on ki, which goes from xi minus 1 to xi. This function, this phi I also is non-zero. You can develop the expression, but it's different from zero also, because you want to enforce the continuity. So you can develop, it's a similar expression. I think you just have to, you'll be able to write it. So it's going to involve hi times hi divided by 2, in fact, and there would be a factorial. I will add them in when I get to the office. I don't want to spend too much time. And then elsewhere, it's 0. Phi I is of x is equal to 0. So these are the 3 conditions that you have to impose your function phi I. And similarly, you can define the 1/2 thing. So if I'm doing, for instance, if I'm doing the phi I plus 1/2, you can do it exactly in the same way. So on ki plus 1 equal to xi plus 1, what do we get? We're getting that phi I plus 1/2 of x is equal to what? It has to be equal at the 2 to 0 at the 2 endpoints. So I'm going to take xi plus 1 minus xi to make it null at that point, but positive on this interval, times what? Times x minus xi to make it null at this endpoint. And the whole thing is quadratic. The product is a quadratic function as it should be. And now what do we have? We have that I need to rescale properly at 1/2. So at 1/2, when I take 1/2, this thing is equal to hi over 2. And this thing is equal to hi plus 1 over 2. So that means I'm getting what? I'm getting hi divided by 2 square like that. Is it square or not? Yes, you have that. So that means you have a factor of 4 coming in front of the function. And what? And phi I plus 1/2 of x is equal to 0 elsewhere. Now you know how to define the functions. You just need to know about Lagrange interpolation, in fact. I hope you all did Lagrange interpolation before. If you took a basic numerical analysis course, in principle, you did that. The only thing is that we do it piecewise, and we're defining the basis function. Remark, as I was saying, of course, you have to do it for all the functions. So not all bases. Not all bases are nodal, even for Lagrange finite element. Of course, if you use a non-Lagrange finite element space, you're having eventually, naturally, a non-nodal basis function. For example, we can have hierarchical basis. So the way you would define that basis is this one. So you use the P1 basis in this way. So you would use what? You would use the at function like that. So you would use the at function, xi minus 1, xi plus 1. So that would be phi I of x. So that's the P1 basis function. And then what you would do is you would do this thing. So to make it quadratic, you would add what? You would add those 2 elements, xi minus 1, xi plus 1. So you would add the one that are quadratic like that over here. So takes the value 1, takes the value 1 here. And then you would add, so this would be what? This would be, I'm going to call it, so phi I plus minus 1/2 and phi I plus 1/2. So the sum of the two, but unfortunately at that point, this does not take the value 0 at that point. So this, you get what at that point at x 1/2, x minus 1/2, you get the value 1/2 at that point. So that means that your basis cannot be nodal in that case, if you do that, because you're having a non-zero value at the middle point. So that means at that point here at x minus 1/2 and at x is equal to x plus 1/2, you're having a contribution coming from these basis element and that one at the same time. Sometimes we do that in this way, even if it's not a nodal basis function. Can I recover the value of the function in that case as well? Unfortunately, you cannot use the value you can recover, you can still apply this formula to recover. Unfortunately, this inequality is not satisfied. You're having this one is still true. That's the way you would compute, but unfortunately, you won't get this to hold, in fact. And since this thing is not holding, you're not having this inequality. This is what is actually giving this thing to hold. This is the critical thing. So with a hierarchical basis, you don't have that. Sometimes we do that. We use hierarchical basis because there are reasons to do it. Okay, so I don't want to elaborate too much at that point. So now where are we going now? So we want to assemble the matrix and see how we organize the data to do that. So this is what is called the assembly process. So let's go to the assembly process. I have my model problem that I rewrite as a variational problem. So let's discuss the assembly process. So what do we want to do? I'm having let me rewrite this as a variational problem because this is what we need. So our model problem is written in this way: u prime v prime plus c u v, like that, on the interval 0, 1 is equal. So in our case, u is going to be in what? U is going to be in h1 0, 0, 1, such that I'm getting what? I'm getting this thing to be equal to fv dx. That's our variational formulation, and this needs to hold for all v in h1 0 omega. So that's our variational problem that I want to assemble. Now, the only thing that you have to do, so you discretize. So you discretize. You build a mesh of the interval 0, 1. You discretize, and then we're going to be, so when you discretize, you just rewrite things on a finite element space. So you're going to be looking for, this is V, this is our set V. So you're going to be looking for U in VH, such that I'm getting what? Such that I'm getting that 0, 1, A, UH, VH. It's easy. Discretizing, it's just adding a H on the unknown, plus C, UH, VH, like that. Dx is equal to F, VH, dx 0, 1, like that. And this needs to hold for all VH in VH. Let's do it for linear element first. So what do we have? We're having what? So when VH VH is the set of linear elements, linear finite elements. That is, I'm using L is equal to 1 in the definition above. So in that case, what do you have? I'm going to rewrite things in this way. So let's rewrite. So this thing is UH, VH, and this is L of VH, this way. So let us rewrite this thing and see how it's going to work. So AUH, VH, I'm going to rewrite on elements. So let me rewrite this on elements. So R is going from what to what? R is going from 1 to capital N, the number of elements, KR. I'm just splitting this integral into its sum on elements, and I'm getting AUH, U prime, UH prime, VH prime plus CUH VH, like that, dx. Now, I want to keep in mind that UH is X is equal to the sum for J going from 1 to n minus 1 of what? Because I'm not including the endpoints because I have Dirichlet boundary condition of UJ phi J of X using the nodal basis in that case. So this thing is solution of and we're having that. And now let's take VH. VH is equal to phi I to rewrite the thing. So what do we have in that case? If I do that, I'm going to have that I have the sum. Yes, the sum for R going from 1 to n of the sum for J going from 1 to n minus 1 of Uj, the integral of what? Kr, and then it's going to be A phi J prime phi I this way prime plus C phi J phi I this way dx. Now we give a name to that. We call this the test function. It happens to be the same as the basis function, but it's not always the case. Sometimes it's different. So the phi j are the basis function. These are the basis function. And these are the test function. They are the same for our problem now, but they are not always the same. Keep this in mind. Okay, now, where is that thing different from 0? It turns out that this thing is only different from 0 under what circumstance? If I look at this is going to be a small thing. This is going to be defining what? This is going to be defining a small matrix. This is non-zero on what? Non-zero when I and j are equal to what? I need to be on the element R. So when I and j are equal to what? Keep in mind the element R is what? The KR is this. KR goes from what to what? KR goes from XR to XR minus 1. Like that. So that means I need to have I and j to be equal to R minus 1 and R like that. So that means I'm going to generate a small matrix. So we can define, so the consequence of which we can then define a local matrix. We're going to call it a local matrix. AR, that is going to be what? That is going to be AR. I have to, yes, I use that notation. And then the I and j, so that's going to be I, j like that. I'm summing on the column here, right? So that means I'm going to have what? I'm going to have this thing. I'm going to have the matrix, which is nothing but KR like that. A phi j prime phi I prime like that. Plus C phi j phi I this way dx. Keep in mind that here is I is the row index and j is the column index. Now, what should be the value? Well, the value should be in principle, we should have ij is equal to r minus 1r. There is no point in actually keeping this index. I just need to know where I'm going to store it in the global matrix, and I'm going to use a local numbering. This is a 2 by 2 matrix, which is a 2 by 2 matrix for linear elements. Okay, so I will figure out later on where I have to put this matrix in the global matrix, but this is a 2 by 2 matrix. From what I have here, it should be indexed by r minus 1 and r, but there is no point in actually keeping the global numbering. I can use a local numbering, so which we will number. So we will number this matrix. We will number this matrix using a local numbering. So we will use a local numbering in the following way. And global numbering as well. So we're going to do it this way. So let me write how it's going to work. So what do we have? So we have our mesh like that. We're starting from x0, x1, x1, x2. We keep going like that. We're having xr minus 1, xr, and then we're going xn minus 1, xn like that. What time is it now? Okay, I still have a couple of minutes. I think I'll have time to. So this is going to be kr, the element kr. This is k1, k2. This is the numbering of the element. Now I'm going to use local numbering. So I'm going to have the node 1, 2, 1, 2 like that. That's going to be the local numbering 1, 2, 1, 1, 1, 2 like that. So this thing is the local numbering. This corresponds to what? The nodes are labeled there by the global numbering. So the global numbering, and I'm having the unknown like that. U0, it depends if I use it or not. If I have a Dirichlet problem, I don't use it. U1, U2 like that. And UR minus 1, UR, and I'm going to UN minus 1. So this is what? This thing. So the global numbering would be what? The global numbering would be attached to these, or if you like, to these here. That would be the global numbering. That's the one who will need to assemble the global matrix. I remember I used this denomination when I was doing finite difference. I had the global matrix, and local matrix I did not mention, but we're going to have it now, and we're going to use the local numbering. So it's going to be with local numbering, since my matrix is 2 by 2, it's going to be ij are going to be equal to 1, 2. But when I have to transfer in the global system, I'm going to need to know where I need to put this. That's an overkill for linear element, but when you get to quadratic element or cubic element, we will need that because there are more degrees of freedom. There are internal degrees of freedom. And moreover, if you want to have a code that can do linear, quadratic, cubic elements, you need to use this approach because I don't know how you can do it otherwise. I don't say it's the only way to structure the data, but that's the most common way to do the structuration. So here we're using the global numbering to label the unknown. So that's global numbering that we're using in this case, but nothing prevents me from saying that on the element kr, I have the local number, the local unknown u1, u2, but to recover the value of these unknown, I'm going to have to have a mechanism to go from local numbering to global numbering, and this thing is going to be called the connectivity table. So that's the connectivity table that contains the information to go from local numbering to global numbering. Now, why I'm going this way, and this is where I'm going to stop because I'm over time. My matrix is non-zero. This little matrix is non-zero on the element kr. So I'm going to calculate the matrix on the element kr using the local numbering, and then I'm going to transfer the information in the global matrix. If you understand this in 1D, when we get to 2D, it's going to be relatively easy, but I will have to organize the information in 2D. It's going to require a bit of care because we will have triangles, we will have quadrangles and things like that. So it's going to be a bit more challenging, but the idea is going to be the same. Okay, so I will define the data structure next time, discuss a bit the assembly. It's becoming very technical. You have to do this slowly if you want to understand. Ideally, I wish to have you to code that once. I know, Anne-Marie, you coded that in 1D. Did you do P1, P2, P3? P1? P1, yeah. So that would have been interesting to have an assignment where I have you to code P2, to write a generic code that can do P1 and P2. That would have been a nice exercise, but that would be, you would take a few days. If you have never done that, you've done, Mohamed? Yeah, it could be challenging. I'm not gonna go in that as far as that. But this is what is done in FreeFM. It's done in the background for you. And eventually, one day you have to get to do it. When I was a PhD student doing finite element, we had to do this manually. Every PhD student doing finite element would get to do that. But these days we use a lot of libraries. It's another yeah.